hello everybody. Welcome to this second Actran acoustic webinar. My name is Zi Zhou. I'm an application engineer and also the product marketing manager at Freefield Technologies, or FFT in short. So FFT is an MSC company and it is the editor of the Actran software. So last time we spent some time to look at the acoustic radiation problem, which is a weakly coupled vibro-acoustic problem. And today we will focus on strongly coupled vibro-acoustic simulations. And in today's agenda, first I will briefly introduce the Actran software suite, then the overview of two-way vibro-acoustic coupling and its main problem types. Then we will look at the some major features of Actran to realize such strongly coupled vibro-acoustics. So these features are the acoustic, structure, and porous element library, the different excitations and boundary conditions, and the solution schemes. Then we will briefly review 4 case studies to illustrate how Actran is applied to real problems in different industries. And then I will guide you through a live demo in Actran VI. Actran VI is the graphical interface of Actran. Then we will have a Q&A session. So first, the Actran software suite. The Actran software is composed of different modules, as we can see on this slide. First, at the bottom, there is Actran Acoustics module. So Actran Acoustics solves pure acoustic problems, such as the sound radiation from a vibrating structure with the vibration already calculated in an FEA solver, for example, in Actran. Actran Acoustics also solves acoustic transmission in intake and exhaust systems, like the image on the right. It solves also acoustic resonance in an enclosed cavity. Now, if we increase the complexity of the problem by combining the acoustics with structure dynamics, we will be solving a fully coupled vibro-acoustic problem. So this module, Vibro-Acoustics, is the topic of today. Then, if we go one step further to combine the strengths of Actran in solving porous materials and the strengths of Actran in solving large but lightly damped structure, then we have the Actran for Actran module. Using Actran for Actran co-simulation, we can solve a fully trimmed vehicle body problem, like this one showing the image. So in such a problem, the body is modeled in Actran, in model approach, and the trim components, they are modeled in Actran in physical approach. Now, if we combine the acoustic physics with fluid dynamics, we start looking at aeroacoustic problems. So this is the purpose of aeroacoustic module that is also available in Actran. And it is used to compute the aeroacoustic sources from unsteady safety results and predict their acoustic radiation. We have also 2 other modules targeted for Actran for aircraft turbofan engine acoustic problem. Now, Actran is programmed using finite element method. So although we have different modules, it is very important to bear in mind that all these modules can be combined with each other. So it is perfectly possible to solve a fully coupled, let's say, aero-vibro-acoustic problem. And all the Actran modules are integrated in the Actran VI, the pre- and post-processor of Actran. So we will see Actran VI in the demo session. Today's topic is fully coupled vibro-acoustics. First, an overview on fully coupled two-way vibro-acoustics. So now this on this page, this schematic image, it shows the idea of two-way vibro-acoustic coupling. So the idea is simple. The vibration of the structure will induce noise in a fluid. This fluid can be a light fluid like air or a heavy fluid like water. On the other hand, acoustics from the fluid can also induce a structure vibration. Now, sometimes it is sufficient to consider only one-way coupling by making some decoupled assumptions, as we did in the last webinar for the gearbox radiation problem. But as a general purpose vibro-acoustic tool, a strong two-way coupling is many times necessary in order to handle the different types of vibro-acoustic problems. So now let's take a look at the main categories of vibro-acoustic problems. First, the interior problems. In an interior problem, a structure is coupled with the inner acoustic cavity. Now, to illustrate this concept, we choose a car side window coupled with the car compartment cavity. In the system, now, if the damping is light and global, we can use a modal approach. This is typically done in the car cavity. However, when the damping is important and localized, for example, in the porous material or in the rubber sealing around the window, we will need to use physical approach. In Actran, we could also combine the physical approach with the modal approach to build a hybrid model. Then exterior problems. It solves sound radiation generated by structure vibration. If the fluid is the light one, for example air, then we can use the decoupled way, as we have already seen last time. But when the fluid is a heavy fluid like water, so the heavy fluid, it will apply on the structure an added mass effect related to its mass. And this added mass effect, it will bring down the structure mode towards lower frequency range. And to simulate this added mass effect, we need to model the structure together with the heavy fluid in a single Actran model with the fully coupled approach. Then other types of vibro-acoustic problems include transmission problems. So this problem solves the acoustic transmission loss through either a single layer structure or a multi-layer structure. In such type of problems, we often apply a realistic random load, such as a diffuse sound field or a turbulent boundary flow model on one surface of the structure. And then we look at the transmitted power on the other side of the multi-layer or single-layer structure. And the ratio between the incident power applied by the random load and the transmission power or the transmitted power on the other side of the structure is called the transmission loss. And transmission loss is the main indicator of the transmission problems. Now the last type is the duct acoustics. In duct acoustics, we have both issues in pipe noise and in shell noise. Pipe noise is a sound that propagates, as we can see on this image, from the duct inlet, going through the entire intake or the entire exhaust system and transmit out of the outlet surface. And shell noise is the sound radiation by the vibration of the duct shell or the muffler shell, like this one, into the free field. We could solve pipe noise and shell noise separately, but when we want to see the whole acoustic picture of an intake or an exhaust system, then we want to combine pipe noise and shell noise in a single Actran model, like this one on the right, with strong coupling from interior acoustics to the shell structure to exterior air acoustics. Now let's take a look at the major features of Actran Vibro-Acoustics to realize those types of problems. First, let's take a look at the Vibro-Acoustic element library. First, because we want to solve a Vibro-Acoustic problem, a first necessary element is obviously the acoustic element, and the simulation of acoustics in Actran is based on the finite element method for acoustic propagation and infinite element for free field radiation into far field. We also have a perfectly matched layer method, or the PML method, which is an alternative method for free field radiation. Because we are based on the finite element method, the Actran model, it can support heterogeneous medium for acoustic propagation, which means we can have a complex background flow of temperature or temperature gradient defined on all the finite element nodes. And on shell elements, first we have the thin shell with 2D element, and the solid shell with volume element, and we have beam element, stiffener element, porous element or rigid body, spring element, point mass that are quite complete in the structure element library. And Actran calculates automatically the global quantities and local quantities both on the fluid element and on the structure element. For example, on fluid elements, we have acoustic pressure as local indicators, or the power radiation as global indicators. And on structures, we have displacement, acceleration as local indicators, and energy dissipation as global indicators. Now take a look on some technical details in the shell in Actran. So on shell element, first we have the 2D shell element, which are surface element. We can use the 2D shell elements to model large and thin structure with flexibility and efficiency. Then we have solid shell elements that are 3D volume element, but with a shell formulation on them. And they can be used to accurately model thick and layered structure with different damping values in different layers. In an Actran model, a 2D shell can be combined with a 3D volume shell. And both shell elements can be coupled with any fluid using either congruent mesh or non-congruent mesh. The coupling with fluid can be done on both sides of the shell, as we can see it is shown by this ship hull problem, where the structure is coupled with air on the left and coupled with water on the right. In Actran, we can also model composite shell, described by a succession of plies, and on each layer of the plies, a fiber-like material can be modeled. This type of material is more and more used in the aircraft material of new generation. And all the shells in Actran, they support static pre-stress effect. And this pre-stress effect, it can modify the dynamic response of the shell. So we can find, for example, related applications in the aircraft vibro-acoustic problem, where the pressure difference when the aircraft is cruising, the pressure difference across the fuselage can induce the shell pre-stress. Now on porous materials. So porous material is a very important and key feature in Actran. By porous material, we mean materials such as foam, rock wool, or fibers. So theoretically, the porous material, they are based on the Biot theory or the Biot model, and the most complete model is the so-called porous elastic model. And this model looks at the behavior of the foam skeleton, behavior of the internal fluid medium, and the interactions between the both phases. And this model is the most accurate one, but it requires most knowledge also on the porous properties. Sometimes we do have access to all the properties that could be measured, but when we do not have access to all of the properties, we can use some simplified models to help. So with less material properties, sometimes the simplified models, you can also offer reasonably accurate results in some specific configurations or at specific frequency ranges. And as in acoustics and structure element, in porous element, a very useful indicator is again the dissipation energy that are both in the skeleton and the fluid in the porous medium. So based on the energy dissipation, we can perform a detailed analysis of the dissipation mechanisms on the porous material. Then on excitations, we can divide the excitations into standard excitations, random excitations, and excitations from import from other external software. So first, Actran, it obviously includes basic excitations, what we call standard excitations, like the mechanical ones, the kinematical ones, and the acoustical ones. And Actran also features real-life excitations. We sometimes call them random excitations or stochastic excitations. The most widely used one is the diffuse sound field that is used to reproduce that diffuse sound field that could occur in a reverberant room in testing, or in the a spacecraft, the chamber for the embarked equipment in a spacecraft during the launch phase. In Actran, there's also a turbulent boundary layer model developed by Caucus. It can represent the effect of the turbulent flow applied on the surface of the structure. Finally, we can also model a delta correlated excitation, which is can be used to model a so-called rain on the roof load. So as I mentioned, Actran can use imported results from FEA software like Nastran, and we can also import from external CFD code, we can import the turbulent, but this turbulent must be an unsteady CFD result, calculated like in example Fluent, Star CCM Plus, PowerFlow, or OpenFOAM, which are the widely used CFD code. Now, on solution schemes, Actran is a multi-purpose tool, and different computational sequences are available. So the most important and widely used ones, first, there is the frequency response analysis, and it calculates frequency response functions like these two curves that we see on this image. And frequency response can be performed either in, sorry, I will show this image first. The frequency response can be performed either in the physical coordinate to accurately represent damping, or in modal coordinate to sometimes to gain computation efficiency. And in Actran, we offer the hybrid method that combines the strengths of both physical coordinate approach and modal coordinate approach. As we can see in this car model, we can model the cavity in the modal coordinate and the window together with ceiling in physical coordinates. We can, in Actran, we also have the model extraction analysis and time domain analysis. All right. When we use the model approach, we can import modes calculated in Actran, for example, that will be fed into Actran, and that will be combined with Actran component. We can also import a super element from Actran into Actran. In Actran, we have very efficient solvers for solving the sparse finite element matrix system. We have direct solvers like MUMS or iterative solvers, and a Krylov solver, it solves the interpolation of results along a wide range of frequency based on results calculated by direct solvers. And different types of parallelization are also available in Actran. The computation on a single problem can be spread on different processors using different strategies of parallelization, from frequency parallelization to domain parallelization or to finite element matrix parallelization. Actran also features the multi-thread calculation capability to speed up solution time. Now we will quickly review some typical applications. First, a typical Actran model in the aircraft fuselage and cockpit problem. A typical Actran model takes into account the real shape of aircraft cockpit and any kind of structure heterogeneity, such as the variable thickness or different materials. And the noise from the exterior is transmitted through the alumni or the composite skin and the multi-layered windows into interior. The skin is stiffened by frames and stringers that are the stiffeners in the aircraft industry. The thermal layer of porous material and the lining layer of shell, they are behind the exterior skin. So these two layers, I mean the porous material and the lining layers, they could provide both noise absorption and insulation. So excitations can be a diffuse sound field, a turbulent boundary layer, or structure-borne engine vibration, or incident acoustic pressure from the propeller noise. We are mainly interested in the noise reduction, or NR, in such a problem. So the NR is a ratio between the incident acoustic pressure on the exterior and the resulting acoustic pressure in the interior cavity domain. And we can see, so this NR curve is divided into different frequency ranges. In low frequency ranges, we have a very pronounced modal behavior, while starting from some frequency, we have entered into a mass law region with a smoothed curve, so less pronounced modal behavior. Now, the next application is the automotive industry. It shows the vibration of a dashboard of a car and the efficiency of some treatment patches that are attached to the dashboard. So the key ingredient in such a model, they are the shell element for the dashboard. It can be a thin shell element with 2D surface element, and in the same model we have the porous and the viscoelastic element that are volume element for the treatment patches. So we can, on these two curves, we can observe a reduced vibration level on this green curve when the patches they are added on the dashboard. Now, if we go further in such a model, we can connect the dashboard with a Nastran super element representing the dynamic influence of the car body. So we can account for the influence of the car body on the dashboard while we perform a local analysis on the dashboard. And next application is again in automotive industry, but it's a duct acoustic problem. It's a transmission loss of air filter in the intake system. The purpose is to compute the transmission loss of this air filter. And in this air filter, we have first the structure of the filter made of plastic, and we use shell elements to model that. And the interior air is modeled with finite element method. The finite element element, and the filter itself is modeled with porous material. And then we will load the acoustic excitation from the intake, the inlet duct, using duct mode boundary condition, and we will apply anechoic, so non-reflection condition, both on the outlet duct for acoustic waves traveling downstream, or and also at the inlet duct, we will apply the same anechoic condition for any reflected acoustic waves traveling back to upstream. And typical results are, of course, transmission loss. You can see that when we compare the green curve with the air filter and the red curve without the air filter, you can see that we have enhanced transmission loss and more a smoother curve when the air filter is installed. We can also perform a power balance. So the idea is the unit energy that is injected into the system, it goes into different channels, different passes. For example, some part is transmitted, some part is reflected back, and some part is simply dissipated in the air filter. So the last example is the loudspeaker problem. So we can see this is a loudspeaker with the box and the cone, the voice core, and the suspension. In a loudspeaker enclosure design, so the box design, sometimes we use a transmission line box like this one. So the acoustic waves on the right side of the cone, when the cone vibrates, we will have acoustic waves with negative phase on the inner side of the cone. And this wave, it will travel through the transmission line. And during this transmission, the negative phase can turn into positive and propagate out of the vent. So this hole is called the vent, and so this this wave, it can complement the already positive wave from the outside of the cone. So the combination of both waves, it can reinforce low frequency performance of the loudspeaker that can be measured on this microphone in front of the loudspeaker. So now when we compare the result, we see that specifically at low frequency ranges, when we compare a long transmission line on the left and the shorter transmission line on the right, we have improved performance in low frequency ranges. This is because at low frequencies, the acoustic wave with longer wavelengths, it has enough distance to travel in the long transmission line. So during this transmission, it can undergo the sign change from negative to positive. So that is all of the presentation. And then I will demo in Actran VI gearbox radiation problem. I will first share my desktop. Okay. So we are interested in the first. What we are seeing is the Actran VI, so the Actran pre and post processing user graphical interface, and we are interested in the acoustic radiation from the vibration of this gearbox. The gearbox is already solved. The vibration is already calculated in Actran. So if you have attended the webinar of last time, you can remember this model. So what we do more in this time is that we will add a cover on the top of this gearbox. So this cover is made of two parts. First, a volume, 3D volume part that is filled with porous material, and a 2D surface element that is a plastic shell. And we want to, well, first to account for the effect of this cover, we need to use the fully coupled vibro-acoustic problem. The vibro-acoustic solution in Actran. And then we can compare the result of this problem with the result of the gearbox radiation without any shell or any porous material covered on it. Now to show you clearly the process in Actran VI, I will start from another Actran VI session. So what we do in Actran is to first import a mesh that is already prepared. So as I import the mesh, we can first identify different parts in the acoustic mesh. First, we have an interior surface of the volume mesh. So the surface is a 2D surface. This surface will receive the vibration information from the gearbox structure, and so it is a starting point of acoustic radiation into exterior field. I will create a domain on this surface, and I call it coupling surface. And then acoustic, it propagates in the volume. I will create a domain on the 3D volume and call it simply air domain. Now, if we look at the mesh from interior, the air domain, it actually doesn't include this shell and porous domain. And this porous and shell domain, they are made in other components. First, this 3D porous domain. So I will create domain, call it porous. And then the 2D shell. I will call it plastic. And then on the exterior surface, we have a surface element for the infinite element. I will create it, a domain, and call it infinite element. And then the last domain will be the clamped condition or the support condition on the around the plastic shell. I will call it support condition. Now I prepared the different domains for the analysis, and then I will specify materials. I can either specify the material properties or just simply import them. Here I will import the material properties, the fluid for the acoustics, and plastic for the shell, and porous for the porous material cover. And we can see as my model is in millimeter, the properties are also in the millimeter tone unit system. In porous material, we can see different categories of properties: fluid properties, elastic properties, interaction between fluid and the structure or the skeleton, and then micro parameters that will activate the frequency dependency of the porous material properties. Then I will continue with the analysis. As we solve acoustic propagation, I will from the structure vibration, I will use the structure vibrations frequency to drive the acoustic propagation. So in the frequency here, I will specify the frequency that comes from the Actran OP2, and then I will select the OP2 file. Okay. Then I will build one by one the component. First, fluid component with the air material. Then the infinite fluid. So again with air material, but here with the properties on interpolation order, center, and axis that are related to the numerical implementation of our infinite element. So I just specify them in this way. And then I will build the porous material, the porous component that causes the porous material, which is applied on this domain. and then the thin shell component on the plastic domain with the plastic properties. Because it's a thin shell, the mesh doesn't have a thickness. We need to specify the thickness of 5 millimeter here. And last, I will build a coupling surface on the interior surface here. So this coupling surface, it will be used on the boundary condition BC mesh. The BC mesh, it will couple this coupling surface with the Actran result. The Actran result, they are imported first from a mesh format, so Actran BDF, and then I will select the Actran mesh, and then the results are in the Actran OP2 here. I'll select the OP2 file. Okay, so this is a model with excitation and auto component. Then I will create the output request. First, I will create some field points that are the virtual microphones. So here I've already prepared the values just for demonstration purpose. I can create a circle arc of microphones like this one, and I can prepare the field mesh, which is the mesh for visualization, map visualization on the different mesh than the computational finite element mesh. Again, I prepare the values, and I will simply add this one. Okay, well, I will not complete all the entries in all the property windows, and I will not launch the computation here. So the idea is that now this model with cover is almost finished. I can launch it, but before launching it, I can show you how to transform this model into another model without cover, which is quite easy. I will simply open the Porous component and change the type from Porous Material into finite fluid material. So now, although the domain is still called porous, but the properties is now air property here. I need also to remove the plastic shell. To do that, I will open the property window of thin shell and then disable it. I will put it into empty component. And then the second model is the gearbox without any cover. Okay, so that was the pre-processing. And then I will show you capabilities in post-processing. Now we are looking at PLT Viewer, which is the tool for 2D plots, so 2D curve plots in Actran. We have loaded the gearbox problem with the shield, or with the cover, and the problem without the cover. So first look at point 45. Which is here on this direction, facing the cover. Can look at some pressure level. This result with cover and without cover. As this one. So blue curve with cover and red curve without cover. We see that at low frequencies there's not too much difference, and at some higher frequencies we start to have difference, especially at 1110 Hertz we have an important difference. And then we can look at directivities around the whole arc at that specific frequency 1110 Hz. Now, to look at the directivity, I will add reverse set, and then now we have frequency tags. So on 1110 Hz, the directivity around the whole arc with cover and without cover. Again, blue curve with cover, red curve without cover. And we can see in polar representation the important reduction by the cover. We can back into Actran VI. We can look at the map. Okay. On the field mesh, and we see visually that at 1110 Hz. Well, first I will change the scale of the pressure map. Then we see that the cover it acts as both the obstacle and absorber on the acoustic transmission. When I apply animate operator, we can change the phase of acoustic propagation to see the acoustic waves propagating in space. Okay, Srinivas, I think that is all of my presentation and demo. We can proceed into the Q&A session.